2.4 is called function characteristics, and what it deals with, for the most part, we're going to talk about even functions and odd functions. The first thing I want to show you is what an even function looks like. An even function is said to be even if f of negative x is equal to f of positive x. And what will happen typically, well, all the time, I guess, with even functions, is that they're going to be symmetric about the y-axis. So if you were to look at this y-axis here, what I mean by symmetric is that it's acting like a mirror. The right-hand side of my function is a identical mirror image, or what we call a reflection, about the y-axis. So that's one way you can look at it and see if a graph is even. It's a mirror image along the y-axis. Another way is what we talked about a few seconds ago, is by using some direct substitution. Now, we all know that f of x is equal to that. Now let's find what f of negative x is. So all I do is wherever I see x, I'm going to plug in negative x. I'll do some simplifying here. Negative x all squared is still x squared plus 2. You can see that I'll highlight f of negative x is the same, identically, as the original f of x. And that follows with the rule for even functions. If the positive x is the same as the negative x, the functions are identical, we're dealing with an even function. Let's look at these examples here. Are these functions even? Now, we don't have a graph to physically show us, so we're going to have to use our theory if f of x has to equal f of negative x. Well, we know f of x is equal to that, so all we need to find now is f of negative x. So I get 2 to the negative x, or to the 6th minus 3, negative x squared minus 4. Simplify. 2 times this stays x to the 6th minus 3, that stays x squared minus 4. You can see that this is the same as the original, so therefore it is an even function. Let's look at the next one. F of x is given as that, so let's now find f of negative x. So I've got negative x cubed minus 2 times negative x squared plus 3. Negative x cubed actually becomes negative x cubed. This will be minus 2x squared plus 3. You can see this does not equal the original function, so it is therefore not an even function. Pretty straightforward, I think. Any questions before I move on? Tony, you're okay?
Yeah, we're good.
Alright. Let's look at odds. An odd function is said to be odd if f of negative x is equal to negative outside f of x. And what we say is these graphs have origin symmetry. Okay, so remember the origin is the 0, 0 point of our Cartesian plane. So it's hard to kind of explain, but if you were to flip that yellow, we'll invert it and flip it along the origin. So the mirror image on this side now will be flipped along the x-axis. So it's a double flip. And that's how they appear to be the same. And if you can kind of picture that again, you're symmetric along the y and the x, but you have to flip on the y and then invert on the x to see that they are mirror images of one another. The easiest way is to simply use this rule here. So I've got f of x, which is the same as y, 10x over x squared plus 1. So that's f of x. Let's plug in f of negative x and see what happens. So I get 10 times negative x over negative x squared plus 1. I'm going to simplify this. This becomes negative 10x over x squared plus 1. Now, we have to look. Is this equal to this? Well, no. So they're for sure not evens. What I have to do is, I'm going to take a negative out of f of x. So I'm just going to take a negative out. And you don't do it to the top and the bottom because that would be the same as multiplying by positive 1. So you can either take it out of the top or the bottom. And if you look at the top, it's the only one that's kind of changed. So you can see that negative f of x does in fact equal to f of negative x. So we prove, therefore, that those two are odd functions. Let's look at some examples that we'll do for ourselves. Here we go. Remembering, if they're odd, let's just do an even here. Even f of x is equal to f of negative x. For odds, f of negative x is equal to negative f of x outside, and neither would be something that doesn't fit either of those particular requirements. So let's look at the first guy here. And what it is. F of x is that, so let's find f of negative x. So I've got negative x to the fourth minus 6 times x to the negative, negative x to the third. This becomes x to the fourth minus 6 times negative x to the third. Becomes x to the fourth plus 6x to the third. Now we have to be very careful with this. I'm going to throw this out there to anyone who wants to volunteer an answer. Is this an odd, an even, or a neither? And explain to me why.
Neither.
Neither. How come, why do you say that? You're right, Ashley. Why do you say that, Ashley?
Because if you took a negative out, it would still be different.
Yeah, if I took a negative out of this, if I took negative f of x, it would be negative, and then you can just use brackets. And if I simplify, I get negative x to the fourth plus 6x cubed. Now this is different than that. You can see simply because of the negative sign on the leading degree 4 variable is opposite in both. So therefore, this doesn't fit any requirements, so it would be a neither. Hey Tony, does that make sense to you guys?
Yeah.
Okay, let's look at B. I'm going to find f of negative x and I'm going to compare it. So I have negative x cubed plus 4 times negative x. So here I get negative. This becomes negative x cubed minus 4x, which becomes positive x cubed minus 4x. Etonia, I'm going to let you have a crack at this one. Is this an even, an odd, or a neither?
It's odd.
Odd, perfect, good job. This one was neither. This one is odd. Now, before I move on to C, I want to look at my little funky bang thing here, reduction identities revisited. This is from Math C30. If you've got cos of negative x, that's the same as just positive cos of x. Its reciprocal, secant of negative x, follows the same pattern. Okay, the negative kind of just disappears. And that reason behind that is quadrant numbers and positive negatives. Sine negative x is actually becomes negative sine of positive x. Its reciprocal, cosecant of negative x, becomes negative cos. Oh, geez. Tony, you haven't gotten this far yet, have you?
No.
Okay, you're gonna have to trust me on this one, okay? This is something called reduction identities, and they'll be taken up in chapter 4 when you guys get there. But for now, I'm glad I typed this one out. We'll follow these. If you've got tan of negative x, it is in fact equal to negative tan of positive x. Remember, these are dealing with degrees, or radians, I should say. But we might not even have gotten to radians yet, so just bear with me. So let's look at C for a second. There's my f of x. Let's find f of negative x. So I've got tan of negative x minus 4 times negative x. Continue on here. Tan of negative x, if you look at that identity, tan of negative x is actually equal to negative tan of positive x. And then I've got a plus 4x there. What would we think? And Tony, I'm going to get you to help me since you're kind of new to this. Is this an odd, even, or neither?
Odd.
Odd, good job. Do you guys, Tony, I'm not sure, I just did this morning, this little reduction identities were visited on here. Yeah, have you guys printed out the notes for 2.4 yet? Tony, have you printed off these notes yet for 2.4?
What's 2.4? What's the title of 2.4?
Function characteristics.
Oh, yeah, we have.
You have these? Okay. This won't be on your notes. So if you maybe want to...
Yeah, we wrote it down already.
Oh, you did? Excellent. Good job. Okay. They will be on the note. They are on Moodle now. I updated them just a few seconds ago, so you should be good to go now. So those, they will help you out when you get your assignments. Westcliff, do you guys remember these reduction identities? Okay. Let's look on to the last little bit here. This is also kind of a review, because I've been talking about increasing or decreasing functions already. A function will increase where its graph rises, and it will decrease where it falls. Now let me look at this graph here. I'm just going to erase my pen here. Remembering that you read a graph from left to right just like you're going to read a book or a sentence from left to right. You can see this graph rises as it goes, and then it hits a situation where it's neither rising or decreasing. But then on the second portion of the graph, we would call this to be decreasing because it's falling from left to right. Nothing probably new for anyone in that case. Now, here it says, if a function increases or decreases for all values in this domain, then it is called simply an increasing and or a decreasing function. So this function that we showed you at the start would not be classified as an increasing or decreasing function because it doesn't change. If I gave you a function, let's say that looks like this, here's my Cartesian point, so we got a line. You could say that this is a constant decreasing function because it's not going to change its level of increasing or decreasing. It's a straight line, so it will always decrease. Hopefully nothing new there. As will this be in terms of B30? One-to-one and many-to-one functions. So what I mean by one-to-one is you've got one x value and only one y value. Many-to-one, okay, will have many x values to one specific y value. And that's what we've got here. They say many y values are repeated, and what I mean by that, let's say if x was 4, y was 3, or for instance, x was 5, y is also 3. That's what the many to one. Or something that you learned in B30, use a horizontal line test. You guys ready for the fancy dancy stuff? Whoa. horizontal line will cross a one-to-one function only once, while across a many-to-one more than once. Let me just show you on a separate slide here what I'm referring to. Here is a function in black that I will draw. And then I'll draw another one in green. Now, with functions, and we're only dealing with functions, so we don't have to bother with the vertical line test. If you remember back to Math 10, a vertical line test determines whether or not you're dealing with a function. In calculus, we're only going to worry about functions, so we don't have to bother with the vertical line test determining if it's a function or relation. But what a horizontal line does is will allow us to provide a situation where we can determine if it's one-to-one or many-to-one. Now, the first function here is a one-to-one because it only crosses my function once. This would be termed a many-to-one because we've got a situation where it crosses here, 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 and if you were to, I guess I didn't continue any of the increasing forms or parts of the graph, so we've got 3 intersection points there. Here's how I describe the many-to-one. If I say x, this point here is probably -5 and 2. This might be 0.5 and 2. And this might be 3 and 2. You can see how there are many x values with one y value. And that's what many-to-one represents. And I think you can probably predict what one-to-one means. Here's your assignment, people. No homework for the weekend because you guys did some excellent work for me today. I will give you some time to work on this in class on Monday. And other than that, try to keep warm and we'll talk to you on Monday.
See you.
See ya.